Hello everyone, welcome to the revision series. This revision is on D and F block elements. D block elements means the last electron enters the D subshell of the penultimate shell. Penultimate shell means n-1 shell, and these D block elements are in groups 3 to 12 with the general electronic configuration of n-1, D1 to 10, ns 1 to 2. And they are known as transition elements because they exist and their properties rather are in between S and P block elements. That is, their properties are intermediate in between S block and P block elements. S block elements are those elements which is on the extreme left of the periodic table. P block elements are on the right of the periodic table. Transition elements are between them. And we have 4 transition series. The first one is the 3D series, which is starting from scandium atomic number 21 to zinc atomic number 30. Second one is the 4D series, which starts with yttrium atomic number 39 to cadmium atomic number 48. The third series is the 5D series, starting from lanthanum 57 and hafnium 72 to mercury 80, because in between there is cerium 58 to lutetium 71, that is getting omitted because that is the lanthanide series. Now next is the 6D series, which begins with actinium atomic number 89 and is still to be completed. It is still incomplete. The general characteristics of transition elements, the first thing, if we compare their atomic radii to that of S block and P block, we can see that they are smaller than that of the S block but larger than that of the P block on account of the difference in the effective nuclear charge. That is, there is atomic radii decreases in the beginning. Why? Due to the increase in the effective nuclear charge. So for that reason, they have a lesser atomic radii than that of the S block elements. But their atomic radii is greater than that of the P block elements, because P block elements have even more effective nuclear charge. But keep in mind that with increase in the number of electrons, where in the n-1 D subshell, the shielding effect or the screening effect of these D electrons on the outermost ns electron also increases. Now this shielding effect is having this order: S greater than P greater than D greater than F on account of the shape of the orbitals. Yes, because S orbital is spherically symmetrical, it is covering the nucleus and actually screening the outermost electron from the nuclear charge most effectively. Now as you move from D to F, the screening effect is also, it has what? Greater screening effect. I mean, it is having, D is having a greater screening effect than that of F. So poor shielding occurs in F than D. So the shielding effect gradually decreases from S to P to D to F. If the shielding effect is decreasing, that means these electrons that are present in n-1 D or in n-2 F, they are not effectively shielding the outer electron from the nuclear charge, and so there is a contraction in the atomic radii. So that we are going to see again later on in details. So atomic radii increases down the group due to the increase in the number of shells, because when you move down the group, the period number goes on changing. That means there is an increase in the shell number. You move away from the nucleus and the effective nuclear charge decreases. But the atomic radii of the elements of second and third transition series belonging to a particular group are nearly the same. Why? Due to lanthanoid contraction, which we are going to see again, which I told regarding the poor shielding effect of the we'll see in the lanthanoid series what is happening in the shielding effect. So let us see. Next, the ionic radii. Ionic radii generally decreases with increase in oxidation state, because if the oxidation state increases, the effective nuclear charge also increases, for which there is a decrease in the ionic radii. Moving on to ionization enthalpy, means the energy, the minimum energy required to remove the loosely bound electron from the isolated gaseous atom. Now, the first ionization enthalpy of the transition elements, they are always greater than that of the S block elements. Obviously, because their atomic radii is also less, but lower than that of the p block elements. Why? Their atomic radii is greater than that of the p block elements. So and in p block elements, the effective nuclear charge increases. That is what is mentioned here. So here again, the effect of the increase in Z effective, that is effective nuclear charge, and increased magnitude of screening effect oppose each other. So the increase in ionization enthalpy along the series is small. Moving on to the metallic character. Metallic character is directly associated with the electropositivity of the element, which decreases from left to right. Because when you move from left to right, the effective nuclear charge increases, and for which what is happening? You need more energy to remove the electron. So electropositivity decreases. Metallic character also decreases. Now these transition elements form metallic bonds. That means the elements that belong to the transition series, they are forming metallic bonds. Why? Because their effective nuclear charge is greater. They have a low ionization enthalpy and large number of vacant orbitals in their outermost shell and greater number of unpaired electrons. Remember to give all the essential points, give the key points that connects one logic, one reason to the other. Now, transition metals are hard and have high density, have high enthalpy of atomization. Why the enthalpy of atomization is high? Because the metallic bonds are quite strong due to the small atomic radii. Moving on to melting point and boiling point. Except zinc, cadmium and mercury, all the transition elements have quite high melting point and boiling point. Why? Because they have strong metallic bonds between them, as the d orbital is partially filled. So they have metallic bonds, they have covalent bonds also. What happens in zinc, cadmium and mercury is they are fully filled, on account of which their bonding is weak. They have no covalent bonding existing amongst them, and so they have low melting and boiling points. Remember one thing, that greater the number of unpaired electron, greater is the tendency to form metallic and covalent bonds. Now, manganese has anomalous melting point and boiling point because its electronic configuration is 4s2 3d5. That means the 4s orbital, it is having fully filled and 3d is half filled. So the electrons are very tightly held and are less delocalized and forms weak metallic bonds than that of the preceding element. So their melting point, that means manganese has anomalous melting point and boiling point on account of its strong electronic or stable electronic configuration or strongly held electrons. Okay. Next, moving on to magnetic properties. Presence of unpaired electron will make the element or make the compound paramagnetic. So transition elements, they show paramagnetic behavior. Why? If they have unpaired electrons, then it will be paramagnetic, and if they have all paired electrons, not even one unpaired electron, then it is diamagnetic. Now, if you compare paramagnetism how you need to compare is you need to see how many unpaired electrons are there. More the number of unpaired electron, more will be the paramagnetic behavior. And seeing the number of unpaired electron by say it is n, you can find the magnetic moment, which is mu is equal to root over of n into n plus 2 Bohr magneton. Now, transition elements, they form complex compounds. Why? Complex compounds means the central metal atom or ion is forming coordinate bond with the surrounding atom or group of atom, which are known as ligands. Why are they capable of accepting these electron pairs from the ligands? On account of its high charge and on account of its availability of the d orbitals, which can accommodate electrons as they are partially filled. So next is catalytic property. Due to the variable oxidation state and due to the larger surface area of the transition elements, they facilitate the adsorption of reactants and hence help in catalytic property. Now, transition elements form compounds which are mostly colored. Why is it so? Because those compounds have unpaired electrons. The central metal atom or ion have unpaired electron. These unpaired electrons, they absorb the visible light from the spectrum, which promotes the electron, within the d orbitals. That means from a lower energy level to a higher energy level within the d orbitals, which is known as d-d transition. So, generally we see when students are answering any question related to color, they just leave the answer mentioning that there occurs d-d transition. That is an incomplete answer. You have to show the electronic configuration. Hence, you have to show that there is an unpaired electron or there are maybe more than one unpaired electron, on account of which they absorb the visible light of the spectrum, promoting electron transition within the d orbitals, which is known as d-d transition. Now, alloy formation transition elements, they form alloys. Why? Because of the similar radii and characteristics or properties. So, they can mutually substitute their position as their radii is similar, so they can mutually substitute their position in the crystal lattice and hence form alloys. The two most important alloys are brass and bronze. Brass has copper of composition 60 to 70% and zinc with a composition of 30 to 40%. Bronze mostly have copper of 80 to 95% and tin 5 to 20%. Next, the transition elements form compounds, interstitial compounds. Why? Because the small atoms occupy the interstitial sites in the crystal lattice. Now, these small atoms, they occupy the voids in the crystal lattice because of the small size of the voids the voids can fit the small size atoms like hydrogen, boron, carbon, nitrogen, these atoms. Now, if you have to answer this question, you have to talk in terms of atomic radii. Oxidation state. All transition elements except the first and the last one of the series, they exhibit variable oxidation state. Why? Because this n-1 d and the ns orbitals, they have comparable energy. And so both the electrons of n-1 d and ns, they involve in chemical bond formation. So the maximum oxidation state in the first series, that is the 3D series, increases from scandium to manganese and then finally decreases. Okay. So metals exhibit, those who exhibit more than one oxidation state, they can also be compared with the standard electrode potential. Now I have given you the example of Cu plus and Cu2 plus. Both are exhibiting +1 and +2 oxidation state, and their standard electrode potential, the reduction potentials, are 0.34 volt and 0.52 volt respectively. So I can see that 0.34 volt is less than that of 0.52, on account of which the Cu2 plus is more stable than Cu plus in aqueous medium. Why? Due to the lower standard reduction potential. Now, when this type of question is asked, that in aqueous medium, see, out of Cu2 plus and Cu plus, which is more stable and why, you have to write all the three reasons. Number one, you have to mention that in aqueous medium, Cu2 plus has a lower standard reduction potential. You also have to mention that Cu2 plus has a more negative hydration enthalpy, or rather the more heat is evolved on account of hydration because the charge over it is higher, and smaller ionic radii. Because the charge is higher, so the ionic radii is also small. Cu plus in the aqueous medium undergoes disproportionation reaction because it is unstable in aqueous medium, and it breaks to form Cu2 plus and Cu. So on account of all these 3 points, Cu2 plus is more stable than Cu plus in aqueous medium. Now, oxides of these transition metals, I have given the example of manganese. Most widely, it has the oxidation states from +2 to +7. So, the lower one is found to be basic oxide, basic in nature. The higher one is acidic in nature, and in between they are amphoteric in nature. Amphoteric means they react with both acids and bases. Now, if you recall the concept of Lewis acids and bases concept, you can see that a higher oxidation state means +7. So it is capable, it has more effective nuclear charge, so it is capable of taking more electron. The Lewis concept makes it acidic in nature. Next, inner transition elements. That means they are located inside the transition elements, and the last electron enters the inner orbital, which we say ultra penultimate shell, which is n-2f orbital. So here it includes lanthanoids and actinoids. Lanthanoids means those 14 elements that are after lanthanum, that is atomic number 57. So what are those 14 elements? They are the 14 elements starting from cerium, atomic number 58, and till lutetium, atomic number 71. The most common oxidation state of lanthanoids is +3. They can also exhibit +2 and +4 oxidation states. The trivalent ions, that is the +3 state, which is the most common state, these ions are colored due to the absorption in the visible region of the spectrum, which results in the transition of the electrons within the f orbitals. So it is FF transition. As we have seen the DD transition, here what is happening is FF transition due to the presence of the unpaired electron, which is undergoing transition by absorbing the visible light, visible region of the spectrum. Moving on to magnetic properties, La3 plus, Lu3 plus, they have electronic configuration 4f0 and 4f14. One is empty, vacant, and the other is what? Completely filled. So they are diamagnetic in nature. They are not having any unpaired electron, but other trivalent ions are having unpaired electron, and so they are paramagnetic. Now, if you have to explain in terms of paramagnetic, diamagnetic, any reasoning, it is better to give the electronic configuration. It is better to show the unpaired electron and hence say it is paramagnetic. If you are unable to write the electronic configuration, at least mention due to the presence of the unpaired electron, it makes it paramagnetic in nature. Next, lanthanoid contraction, which I was just saying that I will be shortly discussing. It is a contraction, that is decrease in the atomic and ionic radii from lanthanum to lutetium. That is the lanthanoid series. Why is it so? It is due to the poor shielding or screening effect of the 4f electrons. On account of this poor shielding effect, it is not able to shield the outer or loosely bound electron from the nuclear charge, and hence the effective nuclear charge increases, on account of which there is a contraction in the atomic radii. Say, due to this, the elements of the 4d series, which we say the second transition series, resembles that of the third transition series, 5d series. So there is a question which is very commonly asked: the atomic radii of zirconium or hafnium, or the properties of zirconium and hafnium are quite similar, though they belong to different series, 4d and 5d. The answer will be on the basis of this lanthanoid contraction. Do explain this lanthanoid contraction which I have explained just now. Now, actinoids are mostly radioactive. They are all radioactive in nature. These elements, they follow actinium atomic number 89 to lawrencium atomic number 103, and they have a more decrease in atomic and ionic radii than that of the lanthanoid series. So actinoid contraction is greater than that of lanthanoid contraction, because actinoid contraction is on account of this 5f electron, which has a poorer shielding effect than the 4f electron which was occurring in lanthanoids. Why? Because 5f is away from the nucleus than 4f. Now, there are certain elements which are very useful, like thorium and plutonium of actinoids. Thorium is used to treat cancer. Plutonium is used in atomic reactors and in atomic bombs. Now, mish metal is an alloy which is of rare earth elements, which is of lanthanoids. In its composition, we can see 50% cerium. So it has 50% cerium mostly, then 25 to 30% lanthanum, 5% of iron, and small amount of neodymium and praseodymium, that is NdPr. Okay, but mostly it has what? Cerium. So it is used in lighter flints, that means gas lighters and all these things. It is being used, and it is also a reducing agent. There are reactions of KMnO4 and K2Cr2O7. Remember, this KMnO4 and K2Cr2O7, they are oxidizing agent. KMnO4 exhibits its oxidizing behavior in neutral, in faintly alkaline, as well as in acidic medium. So here we can see in neutral and faintly alkaline medium how it is exhibiting its oxidizing nature. Here with I-, with S2O3 2-, with Mn2+, keep in mind that in inorganic reactions, complete the following reactions, or what happens when the complete balanced reaction is required, unlike organic reactions. Now, MnO4 2- is paramagnetic in nature, and it is known as manganate ion, having a tetrahedral structure. It's green in color. It has one unpaired electron, so it's paramagnetic. Now, MnO4-, this one is your MnO4 2-, and this is your MnO4-, which is your permanganate ion. It is purple in color, having a tetrahedral structure. So these are the structures. Now, in acidic medium, KMnO4 shows its oxidizing nature, and these are the three examples which I have shown you, with I-, with Fe2+, and with oxalate ion in presence of H+, that is in acidic medium. Now, what happens when KMnO4 is heated? When you heat KMnO4 at 513 Kelvin temperature, it decomposes to K2MnO4, MnO2 and O2. K2MnO4 is potassium manganate. Now KMnO4 acts as a powerful oxidizing agent in acidic, neutral and alkaline medium, which already I have mentioned. K2Cr2O7 acts as a powerful oxidizing agent in the acidic medium, and these are the two examples which I have given you with Fe2 plus and with I minus. Remember to balance them, so you can write the half reactions and then you can write the overall reaction. Follow the half reaction method. Now K2Cr2O7 can be prepared from chromite ore, which is FeCr2O4. This is chromite ore. FeCr2O4 is getting roasted with Na2CO3, that is in presence of Na2CO3 in excess of oxygen. When you heat it, you get Na2Cr O4, which is sodium chromate. This sodium chromate is converted to its dichromate in presence of acid H2SO4, and there is exchange of the cation with KCl to form K2Cr2O7, which is potassium dichromate. This potassium dichromate can be separated by fractional crystallization method. That is the method of separation of two or more soluble solids based on the difference in solubilities in a solvent. So here are the important reactions. You can study couple of more reactions of KMnO4 and K2Cr2O7 and the structures related to this unit from your NCERT. So till then, bye all of you. See you in the next video.